Hello students, welcome back to another session in unit number 4 where we are going to see the psychrometric of air conditioning processes. It is bigger topic, hence I have splitted this into 3 sessions and in 3 more sessions we are going to complete unit number 4. This is the content we have seen in unit number 4, properties of moist air, Gibbs-Dalton law, specific humidity and dew point temperature, degree of saturation and relative humidity, enthalpy, humid specific heat, wet bulb temperature, thermodynamic wet bulb temperature, psychrometric chart, psychrometric of air conditioning processes. This is the topic we are going to see today, and in 2 more sessions also we are going to see the same topic, mixing of air streams. So this is the last topic, and it is obviously one of the psychrometric air conditioning processes only. But we are going to see this as a separate topic, and we will see it in in fourth session from here on. So today we will start psychrometric of air conditioning processes, and this is the first part of this topic, and we have 2 more parts, so that also we will be discussing in detail. First I will list down what are all the air conditioning processes, psychrometric of air conditioning processes, and then we will see all those processes in detail. So here the psychrometric of air conditioning processes, the various psychrometric processes involved in air conditioning to vary the psychrometric properties of air according to the requirement are as follows. So these are the requirements: sensible heating, sensible cooling, humidification and dehumidification, cooling and adiabatic humidification, cooling and humidification by water injection, heating and humidification, humidification by steam injection, adiabatic chemical dehumidification, and adiabatic mixing of air streams. So as I said in earlier slide, adiabatic mixing of air streams, so this topic alone we are going to see as a separate topic. Obviously that is the last topic in our unit number 4. So these are all the processes that we are going to see in detail in 3 parts, and we are starting the first part now. So first is sensible heating. The first topic in this part is sensible heating. The heating of air without any change in its specific humidity is known as sensible heating. So there is no change in specific humidity, then it is known as sensible heating. And let air at a temperature Ta1 passes over a heating coil of temperature Ta3 as shown in figure A. So I will show you that figure. It may be noted that the temperature of air leaving the heating coil Ta2 will be lesser than Ta3. So that is the temperature difference, and I will show you clearly in the diagram. The process of sensible heating on psychrometric chart is shown by a horizontal line 1 to 2 and extending from left to right as shown in figure B. So I will show you the diagram. The point 3 represents the surface temperature of the heating coil. So this is the diagram, and this is the coil, heating coil. So here the air is in, so that is the Ta1, and air is out, so that is Ta3. And now this is the psychrometric process, so steam in and steam out. So this is the heating coil, so that is the Ta3. So Ta3 is obviously is greater than Ta2 as well as Ta1. And now this is the psychrometric chart drawn between dry bulb temperature and specific humidity, and here this is 1 to 2, it is drawn horizontally. So this is the W1 is equal to W2 at this point. The specific humidity at point 1 as well as at point 2 both are equal. So for the enthalpy is drawn here, and when we project it onto enthalpy line, we will be getting H1, H2 as well as for H3. So this is Ta1, TA2 and TA3. So TA3 is the heating coil temperature, and this is the psychrometric chart, and it is usual psychrometric chart, the what we have discussed in earlier topic also. So that is shown separately here. So heat absorbed during sensible heating. The heat absorbed by the air during sensible heating may be obtained from psychrometric chart by enthalpy differences H2 minus H1. So in that inclined line H2 minus H1, so that is the heat absorbed by the air during sensible heating. So it may be noted that the specific humidity during the sensible heating remains constant. So specific humidity W1 is equal to W2, and the dry bulb temperature increases from TA1 to TA2, and the relative humidity reduces from Phi1 to Phi2 as shown in figure B. So that's what we have seen in earlier diagram. The amount of heat added during sensible heating may also be obtained from the relation. So this is the heat added, so that is Q H2 minus H1, enthalpy of zero point 0.2 minus enthalpy of zero point 0.1, and CPA into TA2 minus TA1 plus WCPW into TA2 minus TA1. So that is equal to CPA plus WCPW into TA2 minus TA1. So that is equal to CPM TA2 minus TA1. So the term CPA plus WCPW is called humid specific heat. So humid specific heat, that is what we have seen in the third topic in this unit, and its value is taken as 1.022 kilojoules per kg Kelvin. So thus the heat required Q equal to 1.002 TA2 minus TA1. So that is in terms of kilojoules per kg. So please remember this equation. It will be very useful while solving the problems. So now we see these are the features, silent points you should remember. For sensible heating, steam or heat water is passed through the heating coil. The heating coil may be electric resistance coil. The sensible heating of moist air can be done to any desired temperature. So the sensible heat of moist air can be increased to any desirable temperature also. Next is sensible cooling. So it is also very similar to sensible heating. The cooling of air without any change in specific humidity. So it is also without change in any specific humidity. So that is known as sensible cooling. So please remember there should not be any change in specific humidity. So that is W should be constant for entire process. So that way you should remember, and it is known as sensible cooling. So let air at temperature TA1 passes over a coil of temperature TA3 as shown in figure A. It is also very similar diagram like sensible heating. It may be noted that the temperature of air leaving the cooling coil TA2 will be more than TA3. So TA2 is more and TA3 is lesser here. The process of sensible cooling on the psychrometric chart is shown by a horizontal line 1 to 2 extending from right to left as shown in figure. So in earlier case we have seen from left to right. Now it is drawn from right to left as shown in figure B. I will show you the diagram. The point 3 represents the surface temperature of the cooling coil. So this is the cooling coil. TA3 is lesser than TA2, and the air in and air out. Air in is TA1, air out is at TA2. So this is the refrigerant is going inside the coil, and it is obviously a cooling coil now. So because refrigerant is circulated here, it becomes a cooling coil instead of heating coil in earlier case. Now this is the 1 to 2. So it is drawn from the right side to left side, and W1, that is the specific humidity at point 1 is equal to specific humidity at point 2, and TA3 is lesser than TA2, and Tier 2 is lesser than Tier 1. So this is the difference between the heating and cooling. So you should remember these differences. So heat rejected during sensible cooling. The heat rejected by air during sensible cooling may be obtained from psychrometric chart by enthalpy difference H1 minus H2 as shown in figure B. So that is what we have seen in heating as well as in cooling, and it may be noted that the specific humidity during the sensible cooling remains constant. So that is W1 is equal to W2. The dry bulb temperature reduces from TA1 to TA2 and relative humidity increases from pi1 to pi2 as shown in figure. So that is what we have seen in earlier slide. The amount of heat rejected during sensible cooling may also be obtained from the relation. So it is also very similar equation, and we see here this is CPA plus WCPW is called humid specific heat. So that is CPM, and its value is taken as same 1.022 kilojoules per kg Kelvin, and it is now Q is equal to 1.022 TA1 minus TA2 kilojoules per kg. It is very similar to earlier case. So sensible heat per minute, so it is known as SH. In short, we can call it as SH. For air conditioning purposes, the sensible heat per minute is given as SH. Sensible heat is equal to MACPM delta T, that is specific humid heat, and delta T is equal to VPCPM delta T, that is in terms of kilojoules per minute. So M is equal to V rho, it is actually V rho, and now V is the rate of dry air flowing in meter cube per minute, and rho is the density of moist air at 20 degrees Celsius and 50% relative humidity, that is equal to 1.2 kg per meter cube of dry air. So CPM is humid specific heat. It is obviously 1.022 kilojoules per kg Kelvin, and delta T is equal to TA1 minus TA2. It is the difference of dry bulb temperatures between the entering and leaving conditions of air in degrees Celsius. So by substituting all these values, substituting the values of rho and CPM in the above expression, we get, so the specific heat is equal to V into 1.2 into 1.022 into delta T. So that is equal to 1.2264 into V into delta T. So that is kilojoules per minute. So now we are converting that into kilojoules per second, or that will become kilowatt. So this is nothing but 0.02044 into V into delta T kilojoules per second, or it can be denoted as kilowatt also. So now these are the salient features. For sensible cooling, the cooling coil may have refrigerant, cooling water or cool gas flowing through it. The sensible cooling can be done only up to the dew point temperature, so that is TDP, as shown in figure B, and the cooling below this temperature will result in the condensation of moisture. So bypass factor of heating and cooling coil, we have already discussed that the temperature of air coming out of the apparatus tier 2 will be less than tier 3 in case the coil is a heating coil, and more than tier 3 in case the coil is cooling coil. That's what we have seen in both cases. And let 1 kg of air at a temperature TA1 is passed over the coil having its temperature, i.e. that is coil surface temperature TA3 as shown in that figure, and a little consideration will show that when air passes over a coil, some of it, say x kg, just bypasses unaffected, while the remaining 1 minus x kg comes in direct contact with the coil. So the maybe a little amount maybe overcoming that or without in contact with the coil, so that may be coming out without any impact. So this bypass process of air is measured in terms of a bypass factor. So bypass factor is also to be considered here, and that should be measured. The amount of air that bypasses are the bypass factor depends upon the following factors. So the number of fins provided in the unit length, so that is nothing but the pitch of the cooling coil fins, the number of rows in a coil in the direction of flow, the velocity of flow of air. So it may be noted that the bypass factor of a cooling coil decreases with decrease in fin spacing and increase in number of rows. So that is how the bypass factor decreases by increasing the number of rows. Now we see the salient features here. Under ideal conditions, the dry bulb temperature of the air leaving the apparatus TA2 should be equal to that of the coil TA3, but it is not so because of the inefficiency of the coil. This phenomena is known as bypass factor. So now in simple way you can remember this. So here, because of the inefficiency of the coil, this phenomena is known as bypass factor, and actually the amount of air that is coming out of the coil without any impact, so that includes the bypass factor. Balancing the enthalpies, so that is I will show you a diagram. So cpmta1 plus 1 minus x cpm, so that is balancing at both points. So that is where cpm is the specific humid heat, so that is x ta3 minus ta1, that is equal to ta3 minus ta2, and hence x equal to x can be calculated here. So now ta3 minus ta2 divided by ta3 minus ta1. So here x is called as the bypass factor of the coil and is generally written as BPF, bypass factor. Bypass factor equations. So therefore bypass factor for heating coil, so this is the equation. Bypass factor is equal to Ta3 minus Ta2 divided by Ta3 minus Ta1, and bypass factor for cooling coil, it is Ta2 minus Ta3 and Ta1 minus Ta3. So in reverse, so Ta3 minus Ta2 here, similarly the vice versa here in opposite way, Ta2 minus Ta3, and this is the diagram. So 1 kg of air is in at Ta1. So this is 1 minus x, and x kg is going through the fins, and this is the insulated apparatus. So 1 kg of air out at Ta2, and this is the coil, and Ta3 is the coil temperature. So it may be cooling coil or it can be heating coil also. So further we can analyze this. The bypass factor for heating or cooling coil may also be obtained as discussed here. Let the air pass over heating coil. Since the temperature distribution of air passing through the heating coil as shown in earlier figure, therefore the sensible heat is given out by the coil. So that is equal to Qs equal to UACTM, and where the U is overall heat transfer coefficient. So U is the overall heat transfer coefficient, AC is surface area of the coil, and Tm is equal to logarithmic mean temperature difference. So this is the diagram, and you can see here the Ta1, T D1, T D2 and T D3, and this is how it is varying. The temperature is varying in this diagram. So logarithmic mean temperature difference, we know that logarithmic mean temperature difference is Tm. So that is Ta2 minus Ta1 that is divided by logarithmic of Ta3 minus Ta1 divided by Ta3 minus Ta2, or BPF can be find out from Ta3 minus Ta2, Ta3 minus Ta1. So Tm can be calculated here. So mean temperature. So here Ta2 minus Ta1 divided by logarithmic of 1 by BPF, that is the bypass factor. So substitution and its derivation. Now Qs is equal to UAC into Ta2 minus Ta1 divided by logarithmic of 1 divided by BPF. So that is bypass factor. And we have already discussed that the heat added during sensible heating, so Qs equal to MACPM into Ta2 minus Ta1. So where CPM is the humid specific heat, it is constant 1.022 kilojoules per kg Kelvin, and Ma is the mass of air passing over the coil. So equating these two equations, UAC is equal to MACPM logarithmic of 1 by BPF, and we have the small derivation here, and the logarithmic of 1 by BPF is equal to UAC divided by MACPM, or we can write like this. So logarithmic of BPF, that is the bypass factor, equal to minus, so because it is reciprocal, UAC divided by MACPM, where the bypass factor can be found out. So e to the power of minus UAC divided by MACPM, so that is equal to E minus of UAC divided by 1.022 MA. So this is how we can find BPF. So the performance of heating or cooling coil is measured in terms of bypass factor. A coil with low bypass factor has better performance. So it is always desirable if the bypass factor is as low as possible. Air handling system. So this is one example of air handling system. So this is the from air from clean room, air return air, and this is the air fresh air intake. So this is intake inlet, and this is mixing section, and we have filters. So filters are provided, and preheat coil, and back filter, another filter, and another fan, and we have cooling coil and reheat coil. So this is simple air handling system, and supply air to clean room. So now it is a cyclic process. So now we are taking out of air handling system, and we are supplying into air handling system. So air is circulated in the confined area. So efficiency of heating and cooling coils. The term 1 minus BPF is known as efficiency of coil or contact factor. It is also known as contact factor. It can be a 2 mark question, and thus efficiency of the heating coil. So that is equal to 1 minus BPF. So we have this equation. It can be heating or it can be cooling. Similarly, efficiency of the cooling coil, it is T1 minus Ta2 minus Ta3 divided by Ta1 minus Ta3, and it is for cooling coil. So earlier this is for heating coil, and this is for cooling coil. So we will see numerical problems on this, and these problems are simple only. And now we will see the first example. In a heating application, moist air enters a steam handling coil at 10 degrees Celsius, 50% of relative humidity, and leaves at 30 degrees Celsius. Determine the sensible heat transfer if the mass flow rate of the air is 100 kg of dry air per second. Also determine the steam mass flow rate if steam enters saturated at 100 degrees Celsius and condensate leaves at 80 degrees Celsius. So Ta1 is given, that is 10 degree Celsius. and phi 1 is given, that is 50% of relative humidity, and Ta2, that is 30 degrees Celsius, and Ma mass is also given, mass of air, so that is 100 kg per second, 100 kg per second. So Ts is 100 degree Celsius and Tc is 80 degrees Celsius. So for this is the dry bulb temperature psychrometric chart. So now we have 10 degrees Celsius and 30 degrees Celsius, and this is the 50% of relative humidity line. So from 1 to 2, and the corresponding enthalpies can be found out from psychrometric chart. So that is H1 and H2. So first mark the initial condition of air 10 degrees Celsius dry bulb temperature and 50% of relative humidity. So this is the relative humidity curve on the psychrometric chart at point 1 as shown in figure, and draw a constant specific humidity line from point 1 to intersect the vertical line drawn 30 degrees Celsius by dry bulb temperature at point 2. So now we have to draw at 30 degree Celsius. So now this is a specific humidity is constant here. From the psychrometric chart, enthalpy at point 1 H1, from psychrometric chart we have to find this, and this is coming as 19.3 kilojoules per kg of dry air, and enthalpy at point 2 H2, so this enthalpy is 39.8 kilojoules per kg of dry air, and sensible heat transfer is equal to Ma into H2 minus H1. Now we know H2 as well as H1, and Ma also known, so that is 100 kg per second. So 100 into 39.8 minus 19.3, it is 2050 kilojoules per second. So this is the first one. Next, steam mass flow rate. So from steam tables, now we have to use steam tables. Enthalpy of saturated steam at 100 degrees Celsius, so that is Hs equal to 2676 kilojoules per kg, and enthalpy of condensate at 80 degrees Celsius, so that is equal to Hf, so that is equal to 334.9 kilojoules per kg from steam tables. You have to get these values from steam tables. Thus the steam mass flow rate is equal to ms equal to q divided by hs minus hf. So that is 2050 divided by 2676 minus 334.9. So that is 0.8756 kg per second, and we can convert this into hours. So that becomes 3152 kg per hour. So this is the answer. So that is the steam mass flow rate. So coming to next numerical problem, a quantity of air having a volume of 300 meter cube at 30 degrees Celsius dry bulb temperature and 25 degrees Celsius wet bulb temperature is heated at 40 degrees Celsius dry bulb temperature. Estimate the amount of heat added, final relative humidity and wet bulb temperature. So these are the three parameters we have to find. So that is amount of heat added, final relative humidity and wet bulb temperature. The air pressure is 1.01325 bar. So this is the psychrometric chart. So this is the 30 and 40, and from 1 to 2 this is given data V1 equal to 300 meter cube. So that is the volume is 300 meter cube. So Ta1 equal to 30 degrees Celsius, Tw1 is 25 degrees Celsius, Ta2 is 40 degrees Celsius, Pb is 1.01325. So that is the air pressure is given, and procedure. So now this is the psychrometric chart, same as earlier problem. So relative humidity is unknown, we have to find it, and mark the initial condition of air 30 degree Celsius dry bulb and 25 degree Celsius wet bulb on the psychrometric chart at point 1 as shown in figure. So that is the 30 degree Celsius. Draw the constant specific humidity line from point 1 to intersect the vertical line through 40 degrees Celsius dry bulb at point 2. So amount of heat added, So now V1 is equal to 0.883 meter cube per kg of dry air. So that is the amount of air supplied is equal to MA equal to V1 capital V1 divided by small v1. So that is 300 divided by 0.883. So that is equal to 339.75 kg. So that is MA, and enthalpy at point 1, so that is H1 is equal to 76 kilojoules per kg of dry air. So at point 2, so this we have to extract from psychrometric chart. H2 equal to 86.4 kilojoules per kg of dry air. Heat added is Q equal to MA into H2 minus H1. So that is 339.75 into 86.4 minus 76. So that is nothing but 3533.4 kilojoules. So that is the answer. Final relative humidity, that is the pi. From psychrometric chart, pi 2 is equal to 39 percentage. So that is a little uh, approximately. So 39 percentage is the answer. And wet bulb temperature at final state from the psychrometric chart, TW2 is equal to 27.5 degrees Celsius. So this is the wet bulb temperature at final state. So these are the answers. So we'll see one more numerical on this. The example 3, the air enters a duct at 10 degrees Celsius and 80 percentage of relative humidity at the rate of 150 meter cube per minute and is heated to 30 degrees Celsius without adding or removing any moisture. The pressure remains constant at 1 atmosphere. So determine the relative humidity of air at exit from the duct and the rate of heat transfer. So rate of heat transfer also we have to find here. So this is the given data. TA1 equal to 10 degrees Celsius, pi 1 is equal to 80 percentage. So that is the relative humidity at point 1 is 80 percentage. V1 equal to 150 meter cube per minute, and TA2 is 30 degree Celsius. PB equal to P, so that is 1.013 bar. So that is 1 atmosphere. So this is the psychrometric chart. So point 1 is at 10 degrees Celsius and point 2 is at 30 degrees Celsius. So at relative humidity at point 1 is 80 percentage and relative humidity at point 2 is unknown. Pi 2 we have to find, and H1 and H2 can be find out from psychrometric chart. So relative humidity at exit. So that is the first mark the initial condition of air 10 degrees Celsius dry bulb temperature and 80 percentage relative humidity on the psychrometric chart at point 1. And this, since air is heated to 30 degrees Celsius without moisture addition or removal, it is a case of sensible heating only. So it is a sensible heating process. So draw a constant specific humidity line from point 1 to intersect the vertical line through 30 degrees Celsius dry bulb temperature at point 2. So from the psychrometric chart, phi 2 equal to 23.5 percentage. So that we have to find from psychrometric chart. So rate of heat transfer, specific volume at point 1 equal to, that is Vs1 is equal to 0.81 meter cube per kg of dry air, and enthalpy at point 1 H1 is 26 kilojoules per kg of dry air. Enthalpy at point 2 H2, that is 46 kilojoules per kg of dry air. So this we are finding out from psychrometric chart. So amount of air supplied MA equal to V1 divided by Vs1. So that is equal to 150 divided by 0.81. So that is the Vs1 specific volume at 0.1. So that gives the MA as 185.2 meter cube per minute. So the rate of heat transfer Q equal to MAH2 minus H1, and that comes as 3704 kilojoules per minute. So this is the heat transfer, relative heat transfer. So numerical 4, we will see one more example, and this is atmospheric air at with a dry bulb temperature of 28 degrees Celsius and wet bulb temperature of 17 degrees Celsius is cooled to 15 degrees Celsius without changing its moisture content. So find original relative humidity, final relative humidity and final wet bulb temperature. So we have to find three parameters. One is original relative humidity, final relative humidity and final wet bulb temperature. So the given data is TA1 is 28 degrees Celsius, TW1 equal to 17 degrees Celsius, TA2 equal to 15 degrees Celsius, and now this is the 15 and 28. So point 1 is uh, 28 degrees Celsius and 15 degrees Celsius is point 2, and for this at 28 degree we have 17 degrees Celsius. So now this is the saturation curve. On saturation curve it is 17 degree Celsius. So it is related to cooling. So it is cooling process, sensible cooling process. The initial condition of air is 28 degree dry bulb temperature. So this is the dry bulb temperature and 17 degree wet bulb temperature. So this is the wet bulb temperature at 17 degrees Celsius is marked on the psychrometric chart at point 1. Since the moisture content remains unchanged, draw a horizontal line from 1 to meet 15 degree Celsius of dry bulb temperature at point 2. So now from dry bulb temperature we have to get point 2. So original relative humidity from psychrometric chart, it is pi 1 equal to 34%. So this is the pi 1. So this is 34% of line, inclined line, and relative humidity, final relative humidity is pi 2. So that is 73%. So this is pi 2, it is 73%. Now we have to find the final wet bulb temperature. From the psychrometric chart, TW2 is equal to 12.2 degrees Celsius. So all this data we can obtain from the psychrometric chart, provided you have to carefully take the values from psychrometric chart. So another example, the moist air is heated by steam condensing inside the tubes of a heating coil as shown in figure. So the part of the air passes through the coil and part is bypassed around the coil. The barometric pressure is 1 bar. Determine the air per minute in meter cube which bypasses the coil and the heat added by the coil. So this is the coil. Now this is the inlet and this is the outlet. Outlet, it is taking place at 24 degrees Celsius and the inlet is 5 degrees Celsius and 60 kg per minute. It is the specific mass, and 100 percentage of relative humidity, and the coil is having relative humidity is 20 percentage. Steam heating coil, it is the heating coil. Now it passes through the coil and there is a bypass also, so that we have to find. And this is the psychrometric chart, that is dry bulb temperature versus humidity, and this is the 100% saturation curve, and this is 0.1 is on 100 percentage, and 20 percentage of relative humidity line, so that becomes 0.3, and 0.2 is at 24 degrees Celsius, and this is the specific heat, and this is the TD3, and H1 and H2 we have to find from psychrometric chart. So given data is MA equal to 60 kg per minute and TA1 is equal to 5 degrees Celsius, pi 1 equal to 100 percentage and pi 3 equal to 20 percentage, TA2 equal to 24 degrees Celsius, barometric pressure equal to 1 atmosphere. So we have to mark initial conditions at 5 degree Celsius dry bulb and 100 percentage RH, so that is relative humidity at 0.1 on the psychrometric chart. Consider 1 kg of air admitted at point 1. Let x kg of air bypasses unaffected and 1 minus x kg passes over the heating coil, and the heating coil rises the air to dry bulb temperature TA3 at state 3. Final air condition at 24 degree Celsius dry bulb with 20% of relative humidity is obtained by mixing bypassed and heated air. So enthalpy values from the chart, so that is TA3, dry bulb temperature leaving the coil is 30.8 degrees Celsius, and enthalpy at point 1, that is H1 equal to 19 kg per kilojoules per kg of dry air. Enthalphy at point 2, H2 equal to 38 kg per kilojoules per kg of dry air. Enthalphy at point 3 equal to H3 44.8 kilojoules per kg of dry air. So the results now you can see the using bypass factor x equal to TA3 minus TA2 divided by TA3 minus TA1. So that is 0.264. So that is the bypass factor, and air bypass equal to x into MA. So multiply BPF bypass factor into 60. So that is 15.84 kg per minute, and heat added by the coil so equal to Q equal to MA H2 minus H1. So that is equal to 60 into 38 minus 19, that comes as 1140 kilojoules per minute. So this is the answer. And next example is the atmospheric air at 760 mm of Hg, dry bulb temperature 15 degrees Celsius and wet bulb temperature 11 degrees Celsius enters a heating coil whose temperature is 41 degrees Celsius. Assuming the bypass factor of heating coil is 0.5, determine dry bulb temperature, wet bulb temperature, relative humidity of air leaving the coil. Also determine the sensible heat added to the air per kg of dry air. So this is the psychrometric chart drawn for this, and given data is Pb equal to 760 millimeters of Hg and Ta1 equal to 15 degrees Celsius, Tw1 equal to 11 degrees Celsius, Ta3 equal to 41 degrees Celsius. So bypass factor is also given, that is 0.5 only. So for this given data, and this is the TA1 15 degrees Celsius and TA3 is 41 degrees Celsius. So TA2 is unknown, so that we have to find, and it is 11 degrees Celsius, that is dry bulb wet bulb temperature. So the initial condition of air entering the coil at 15 degree Celsius dry bulb and 11 degree Celsius wet bulb temperature is plotted on the psychrometric chart at point 1. A constant specific humidity line is drawn from point 1 to intersect the vertical line through 41 degrees Celsius dry bulb temperature at point 3. So the point 2 lies on the line 1 3. So this is 1 2 3. So point 2 can be located here, and the corresponding temperature also can be found out. And the calculations, dry bulb temperature leaving the coil is Ta2. So that is the dry bulb temperature at the air leaving the coil, and the bypass factor is 0.5, and Ta3 minus Ta2. So we know BPF, we know Ta3, we know Ta1. So we can find out Ta2. So that is equal to Ta2 is equal to 28 degrees Celsius. So wet bulb temperature of air leaving the coil is from the psychrometric chart Tw2 equal to 16.1 degrees Celsius, and relative humidity of air leaving the coil is from psychrometric chart Pi2 equal to 29%, and sensible heat added to the air per kg of dry air, so that is equal to H2 equal to 46 kilojoules per kg of dry air. So this also we have to find from the psychrometric chart only. H1 equal to 31.8 kilojoules per kg of dry air. So thus sensible heat added equal to H2 minus H1, and that is 46 minus 31.8. So that is 14.2 kilojoules per kg of dry air. So this is the answer. So now we have completed this part, and we will see the next part in the air conditioning processes, psychrometric of air conditioning processes, and we will see in next session, students. So coming to references, these books you can refer Kurmi. Kurmi book is very simple to refer, and this topic I have taken from Kurmi book only. So please refer this. For additional information, you can refer Aurora as well as R.K. Rajput. So we stop here, and we will start the part 2 in this topic in next session. Thank you, students.